Hello everyone, welcome to Physics by RN. As you know, we have started the free lecture series for JEST exam. These lectures are designed in such a way that you can complete the JEST syllabus at a very fast rate, and also if you do not have a very much knowledge of the basics, you can still understand the lectures and you have a very best chances of qualifying the JEST exam. Your task is to complete all the lectures by watching all the lectures and completing the PYQ questions. So statistical mechanics, quantum mechanics, classical mechanics lectures are already being uploaded. These lectures are not very long and lengthy, but instead only the important parts which are needed for the JEST are covered in these lectures so that we have the best chance to qualify the JEST exam. Today I am starting the electromagnetism classes. So in the first class of the electromagnetism, I will teach you few things and few things I will give you as an homework to complete, since those things are very easy and you can very easily do by reading the book or watching so many infinite amount of videos which are already available. I will cover the part that has not been covered anywhere else or which is very much needed for the JEST exam. So let's begin. Before we start the electromagnetism, uh, the first topic which comes to the mind when we start electromagnetism is electrostatics. Now, in order to understand electrostatics, you should definitely know the topic of spherical and cylindrical coordinate systems. So, what are the things that you should know in this? First of all, what are the surface elements? What are the volume elements? What are actually spherical and cylindrical coordinate systems? What are the how do we define them mathematically? Then, what are the divergence and curl in the spherical and cylindrical coordinate system? I have made an entire video on this, which is available on the YouTube channel. Please go and watch that video first, if before continue to continue the electromagnetism. Okay, so watch that video first. That will be very much beneficial. Now, let's assume that you know the spherical and cylindrical coordinate systems. Moving on, the first topic that comes in electrostatics is electric field. Now, this is a very easy topic. We have been studying this topic since the class 11th, 12th. So I will not cover this part as such because it's very easy. You can very easily do it. But I can tell you what are the things that you should do in this topic. So when we say electric field, number one thing that you should know is what is electric field. I assume all of you will know that. If you don't know that, start by reading the Griffiths book, DJ Griffiths book, chapter number 2. So I will suggest each one of you to read this chapter very thoroughly from the very beginning, that what is electric field, what are the units of electric field, okay, how do we define the electric field, and then find the electric field for these charge distributions. So there are two kind of charge distributions. Number one, discrete charge distribution, in which dipole comes. Okay, discrete charges means there are few charges placed in a space at some points. For example, dipole. Okay, we know there is minus q charge plus q charge separated by amount a, and you have to find the electric field at the axis and at the perpendicular to the axis. So very simple derivation. It is given very nicely in the DJ Griffiths book. You can easily solve these kind of problems by just reading the book. It is class 11, 12 syllabus. You can easily understand that. Okay, another thing is continuous charge distribution. There are two kinds. One is ring and one is disk. These two problems are very important. The detailed solution is given in the DJ Griffiths book. You can go and read it. It's quite easy. Let's say I have a ring, and on the ring, positive charge has been distributed. What will be the electric field on the axis of this ring? Similarly, I can say this is the same thing about the disk. So both the things you will easily find in the DJ Griffiths book. So whatever problems, solved examples and unsolved examples in between the chapter of the DJ Griffiths book is given, please go through those. That will actually give you a very good idea that how to solve the problems. It's a good revision for class 11th and 12th. So start with that. These kind of questions have actually came in the JEST exam, and electrostatics is a very easy part which can be covered, and it actually gives you very good amount of marks in the JEST exam. From where I will begin is Gauss's law. So now you will very soon find that it is not possible to find electric field for all sort of charge distributions. So what we do then? So Gauss's law gives us an easy way to find the electric field due to the complex problems, complex charge distributions. So what does Gauss's law says? Gauss's law says that, okay, mathematical definition is closed surface integral of electric field. So I will repeat, closed surface integral of electric field on some closed surface. Okay, it's a it or I can simply draw the globe. Okay, this is your globe. This is your globe. So you can now imagine it as a three-dimensional object. Okay, so this is a closed surface. Whenever some surface is closed, it gives a volume. It gives rise to a three-dimensional object. So the flux of an electric field through this closed surface. What is flux? So electric field, when you will study, I will not go in a deeper detail because we want to just touch the important parts for the syllabus. But the flux is, what is an electric field per unit area passing through this surface. So let's say there is some charge enclosed in this surface, plus Q. Okay. Now this plus Q charge will give rise to the electric field, which you all know will be something like that. Something like that. Very easy. Very easy. Electric field lines will be something like that. So what is this electric field lines per unit area? So if you see, if this is a sphere I draw, how many number of lines are passing through this area? So that will give rise to a flux. So number of electric field lines passing through any given area gives you the flux at that point, or flux through that enclosed surface. So that is what the definition is. So flux through electric flux through any closed surface is equals to how much charge is present inside that. Okay, that it will directly be proportional to what is the number amount of charge that is enclosed in that. Now this is class 11 12 trivial information. Okay, Gauss's law. So if you read a DJ Griffiths book, you will have a greater idea that what is Gauss's law in detail. I will today touch that how do you solve the problem using this equation, and how in JEST exam the problems have came from this equation. Okay. Number one problem is Cartesian coordinate symmetry problem. So our electric field is given in Cartesian coordinates. So Cartesian coordinates you know is x, y, and z. So these are Cartesian coordinates. So when we have a Cartesian coordinate symmetry, how do we actually solve the problems? So electric field is given to you as k under root x x cap. So your electric field is along the x cap, and you are asked that this is a surface in front of you, and what will be the charge enclosed in this surface. So electric field is given, charge enclosed is asked. So directly we know that Gauss's law should be applied. So how do we actually solve this problem? So if we have to find q enclosed, we actually have to find the E dot ds. How do we find the E dot ds? Now ds, if you see, ds is a area element, area element on the surfaces. So let me just remove this and draw it again. Now you see how many areas you see, how many surfaces you are seeing in this object. So two surfaces which you see is in the x direction. So one surface is this, let's call this one, and one is on the back side, so let's call that two. Two surfaces if I see is along the y cap. Okay, so let's call this one, so 3, and let's call this 4. And two surfaces are along the z cap, so let's mention this as 6 and this as 5. So now these small areas, if I draw on the total area surface, small surface on this total surface is actually said as ds, this small surface patch. Now if you see the direction of this ds vector, it is perpendicular to this small surface patch. This is how we define ds vector. How do we define ds vector? The small patch on the surface, and the direction of this vector is perpendicular to this small patch. So what will be the direction of this vector 5 and 6? It will be along z cap and minus z cap, right? What will be the direction of this small ds patch in third number? That will be plus y cap, and along 4 will be minus y cap. And along 1 and 2, if I ask, in along 1 it will be plus x cap, and along minus it will be minus x cap. The directions, I'm only talking about the directions. Now if you see carefully, the electric field, it is along the x cap. So when I take the dot product of E vector with 4 and 3, it will give me 0 value, because y cap dot s x cap is 0. Similarly, if I do the dot product with 5 direction, surface 5 and surface 6, it will again give me 0. Why? Because z cap dot x cap will be 0. Only non-zero terms will be along the x cap, that is surface 1 and surface 2. So let me remove all other surfaces and then only look at the surface 1 and surface 2 in order to have a better understanding. So these are the two surfaces that will give me the negative, that will give me the non-zero values, right? So I have written this my E dot ds closed surface. Closed surface means all 6 surfaces combines to make a closed surface. So only two terms will be non-zero, which will be E dot ds1 plus E dot ds2. Now what is ds1? So what will be the small patch on this surface? It will be dy dz. Because in this surface, if you see this surface very carefully, your x is fixed. X is fixed. And what is the value of that x? X value is 2l. You can very easily see, if I remove this, you can see this distance is l and this distance is l. So the total distance is 2l. Your x is 2l, but your y and z is changing. So your small patch on this surface will be dy dz, okay, dy dz x cap, and your x value on this surface is 2l. Similarly, if you see d, and the direction will be along x cap as we discussed. If you see the surface 2, your ds will be dy dz, but the direction now this time is minus x cap, perpendicular to it and going away from the surface. That will give you minus x cap. And your x this time is l, because this distance only is l. Now let's put the value here. E we already know is k root 2x. Oh, sorry, k root x. So let's put the value. So x value here is, sorry, so x value here is 2l. So I put x value as root 2l, and I put the value of ds as dy dz. Similarly here I put the x value and dy dz. If I do the very simple calculation, and I know that dy and dz are going from 0 to l. If you see this surface, it is changing, y is changing from 0 to l, 0 to l, and your z is also changing from 0 to l. So 0 to l, and it will give me the answer as root 2 minus 1 kl 5 by 2. So this is what, this is my E dot ds. But what I want to find, I want to find q enclosed. So what is q enclosed? It will be epsilon naught times E dot ds. Very simply, I will just multiply it with epsilon naught and I will get the answer. Let's check which option is correct. So your option D is correct here, right? So this is how you solve the problem when it is in the Cartesian coordinates. Now, how do you solve the problem when it is in radial coordinates? Okay, I already mentioned you should know very deeply about the radial coordinates, spherical symmetric coordinates, and the cylindrical polar coordinates. So now let's see the radially symmetric problem. Now this is radially symmetric problem. How do we know? So electric charge distribution produces an electric field. So electric field is given to you, and this electric field, if you see, is only function of r. Only function of r. So if I draw a sphere with radius r, on the surface of this sphere where r is fixed, At all these points, R is same. It means electric field is same on all these points. It means electric field only depends upon the radius R. That it means electric field is radially symmetric. Okay, so our electric field is radially symmetric. How we can find the net charge? Again, the same problem. So it is given that you have a sphere of radius 1 by alpha. And what is a charge enclosed in this surface if this is the electric field? So electric field is given to us and we only want to find the radius of this sphere. I will again find the E dot ds. But now these kind of problems, it is best you use the spherical coordinate system instead of Cartesian coordinate system. What is ds in the spherical coordinate system? So there are now similarly ds can now be in the three directions. It can either be along the r cap, theta cap and phi cap. Similarly to the last problem where we saw our ds vector was either along x cap, y cap or z cap, and we only choose along the x cap because that was giving us a non-zero value because our electric field was along the x cap. Similarly here our dx vector can be either along r cap, theta cap and phi cap. But looking at this electric field, we know we only have to keep ds vector which is along the r cap. What does it mean? We only have to find the patch which, which is perpendicular to the this our surface. So if this is a surface and these patches we will take which will give us the ds vector perpendicular to this surface. So this will give you the ds vector along the r cap. So r cap always remember is like this, perpendicularly penetrating the spherical surface, right? So in spherical coordinates, ds is written along r cap as r square sine theta d theta d phi. Because now r is fixed, what is changing is d theta d phi. This is what we saw. When our ds vector is along x cap, what was changing? Dy dz. So here r cap, it is along r cap. So what will change? D theta d phi. And it is written as r square sine theta. How this came, you should see the lecture on the spherical and cylindrical coordinate system. So you exactly know how this is come. Okay, so you should know how to write these kind of surface elements and the volume elements. This is very important. Okay, I will not go in detail in this video because I have made the separate video for that. So now let's do the ds e dot ds. So now e I have written as 1 minus e raised per minus alpha r cap by r square, which is given, dot r square sine theta d theta d phi r cap, right? So just a very simple integral, right? 1 minus e raised by, so this r square and r square will cancel each other. Okay, and 1 minus e raised per minus alpha r sine theta d phi. Your d theta, so your theta varies from 0 to pi, that you should know if you know the spherical coordinate system, and your phi changes from 0 to 2 pi. And your r is fixed because radius of the sphere is given already. It is alpha minus 1, that is 1 minus 1 by alpha. So I have put the value of r. I am doing this integration, very simple integration. I will get this value, 4 pi 1 minus e raised per minus 1. Similarly, if I want to find the charge enclosed, I will just multiply epsilon naught with this and I will get the charge enclosed. Very simple question as that. Only thing that you should know in this is how you write the area element in the spherical coordinate system. If you don't know that, watch the video. Okay, now let's move on. Another, I before, okay, so these were the just PYQs. So you see how easy questions are coming from electrostatics. If you actually want to study the Gauss law and understand the Gauss law, only two problems are enough to understand the entire Gauss law. So I have the two fundamental problems. One is annular sphere, or you can say the problem in the radial symmetry, and another is the annular cylinder, which is a problem in the cylindrical symmetry. So let's first see annular sphere. What is annular sphere? So there is one inner sphere of radius a, and there is one outer sphere of radius b, and there is a charge in this. So what is, when I say sphere, so you should assume like it is a dielectric sphere, okay, not a conducting sphere but a dielectric sphere in which the charge can be stored. So charge is present here, and the charge density is only present between the two spheres, only between the two spheres, not outside and not here inside, not less than a. Okay, it is between a to b, and this charge density is not uniform, it is kr. It depends upon the distance from the origin or the center. Okay, what does it means? So if you see close to this area, the charges are far apart, it means charge density is less because r is less. But if you increase the r, charge density increases, it means the charges comes more close. Okay, so this is how your physical picture is. How do you find the electric field for such configuration at 3 points? One is r is less than a, means inside, then r is between a and b where the charge is present, and then r is outside. So for all three, we will again use the Gauss law. So what does Gauss law say? E dot ds closed integral should be 0. Now for r less than a, I will assume the Gauss sphere. So whenever we find the electric field, in last two questions what we did was, electric field was given to us and we were finding the charge. Now the charge density is already given to us and we are finding the electric field. When we do that, what we do is we assume a pseudo Gauss surface, imaginary Gaussian surface, and we choose a surface in such a way that it matches with the electric field symmetry. Okay, electric field symmetry. So here charge density is radially symmetric because it only depends upon r. So we are assuming it to be a Gauss sphere. Gauss surface. We are assuming it to be a sphere again. Okay, that is a reason. Okay, because this kind of charge density will give rise to the electric field in the radial direction. In the radial, so you can assume, you can very easily see that. Okay, so electric field will be something like this in the radial direction. That is the reason we are choosing as a Gaussian sphere, not Gaussian cylinder or Gaussian plate or anything. Gaussian cube, nothing. We are choosing Gaussian sphere because electric field produced by such charge densities is radially symmetric, or you can say along the R cap. So first thing which we are assuming is your electric field that will be produced will be along the R cap. It will not be along theta cap. It will not be along phi cap. It will be along the R cap. And you should think about it. Why electric field will only be along the R cap? This is a very good interview question. You should read the Griffiths book and think about it. Why? For such radially symmetric charge densities, why electric field will only be along the R cap? But here we are assuming that it is only along the R cap. Now let's begin. So I assume the Gaussian sphere inside this area because R is less than A. And you see in this Gaussian, imaginary Gaussian surface, there is no charge enclosed. So if there is no charge enclosed here, electric field will come out to be 0. So electric field is 0 for R lesser than A. Now let's find for R greater than A but less than B. So in between the body. So now you have to first find E dot ds. Very simple. Again, we know that ds is r square sine theta d theta d phi. The same thing we did in the last problem. So E dot ds, if you see, will be E times r square. R is fixed here, right? So only theta and phi is changing. So you can easily find this thing and you will find that 4 pi r square E. Very easy. Very easy thing. The main thing is how do you find the charge enclosed in this Gaussian surface? So charge enclosed, you know, is equals to the rho dV, volume integral of charge density into volume. Okay, volume integral of charge density, right? What is dV? Volume element. So let's say I assume a small volume in the sphere. What is that small volume is? That is r square sine theta dr d theta d phi. You should know these things because it is very important. You should see the spherical polar coordinate systems and you should know this. So I will just now put the values. So rho value is kr, okay, and dv value is r square sine theta dr d theta d phi. Now let's see how it comes out. So this comes out r cube dr sine theta d phi. Okay, and you see r cube, r, your r is changing from a to r, not from 0 to r. You can see here actually your r is changing from a to r. Why? Because your charge density is only in region from a to r. Charge density is not present in below a. So you have to take the limit of r from a to r, not 0 to r. Similarly, sine theta goes from 0 to pi, phi goes from 0 to 2 pi. If you solve this and if you put in the Gauss law, you will find the electric field to be this. And in the vector form, you only have to put r cap because we already assumed that electric field was in the direction of r cap. So if you carefully observe, the numerator is r raised to power 4 and the denominator is r square. So your electric field is increasing in this area by the factor of r square, right? So your electric field was 0 for r less than a, and your electric field is increasing by amount r square in the area a to b. So look at this mathematics very carefully. I will put these notes in the Telegram channel. You can download these notes and carefully observe the mathematics that has been done here, and you should know this kind of mathematics. How do you practice such mathematics? There are many problems which are given in the DJ Griffiths book. You should solve all of those problems, then you will be able to understand what mathematics is going on and you will get a very good practice. Okay, now let's complete the problem by solving the electric field outside b. How do you solve that? E dot ds equals to, again, 4 pi r square e. This is simple, we already know. But what is charge enclosed? Similar thing here, r k r cube sine theta, same integral we are getting, but now that only the limits will change. So you see the charge density is only present from A to B. It does not matter even if your Gaussian surface is outside this B. So let's say this is A, this is B, and your Gaussian surface is outside B. But doesn't matter. Your limits will only go from A to B. Why? Because charge density is only present from A to B. Okay, so you put the value from A to B, then again solve the values, and this time you found that your electric field is reducing by R square. Okay, because this r square will go and become the denominator there, and here numerator is do not have r, it is constant because limit only goes from a to b, so it is constant. So your electric field is reducing by the amount r square. So how do we summarize this? So your, for r less than a, electric field is 0. For a to b, electric field is r square. For r to b, it reduces by r square. So if I plot this, this kind of plot will come out. Till a it is 0, then it increases by r square and then it decreases by r square. These kind of plots can be asked in the JEST exam. And this kind of mathematics is very important. You should know this kind of mathematics very well. So this is just to give you a hint and so on so that you can proceed from here. These are not the detailed and going on lectures. Okay, so you can get an idea that how you can actually solve the problems. Now, similar problem is annular cylinder. So there are two cylinders. So inner cylinder and outer cylinder. Inner cylinder has radius A, outer cylinder has radius B. Inside inner cylinder, there is no charge, and the charge density is only between the inner cylinder and the outer cylinder, and it is given by Ks. S is the distance from the axis. Whenever we define the distance from the origin, we say R, and whenever we define the distance from the axis, we say S. This is a common nomenclature which is being used. Okay, so charge density is Ks. Again, as we are moving away from the axis, the charge density is increasing, right? And it will only increase till here, till B, and then it will become again 0. It is not outside the cylinder. Okay, so what will be the electric field inside the inner cylinder? It will be 0 because again charge enclosed is 0. Now again similar mathematics, what will be the electric field between A to B? So first let's find the charge enclosed. It will rho dV. Now what is the dV in the cylindrical coordinate system? Now we are moving from spherical coordinate system to cylindrical coordinate system. So your dV will be S d phi d ds, d phi, dz. So you can get these numbers, these equations from the lecture which I have given on the cylindrical and spherical coordinate system. You should know these things. So let's just put it. Rho is ks, dv is this. Your s is changing from a to s, not from 0 to s. No, because your charge density is only from a till this surface s. Okay, from a to s. Just put the values, then you get the charge enclosed like this. And what is your E dot ds? E dot ds. Now here we are assuming that E is cylindrically symmetric because your charge density is cylindrically symmetric. It means it is perpendicular to the axis. Okay, it is cylindrically symmetric. It is along the S cap, right? So what is your ds vector along the S cap? It is S d phi dz. Just putting the numbers E, S, d phi dz, you will get 2 pi E S L. L is the length of the what do you say, your cylinder. So just put in the Gauss law 2 pi E S L, and on the right hand side your charge density, you will get your electric field like this. So your numerator is increasing by S cube and your denominator is S, so your electric field is increasing by S square. Okay, so inside A, electric field was 0. Between A to B, your electric field is S square. How do we get to this equation? That is very important. Look at the mathematics by slowing down, looking at the PDF given in the Telegram channel, solve it by yourself and get to this equation. Okay, I do not want to do the algebra steps for you. Very easy. You should know how to get these numbers. Okay, how to do these derivations. It is just a matter of practice, right? Now, what will happen for S greater than B? For S greater than B, similar thing, charge enclosed, same integral, but now the limits of integration is not from A to S, but it is from A to B, right? So this was your B and this is your actually S. Okay, so it is not from A to S, it is either from A to B, because till only B your charge density is present. Similar to the last problem, right? So you put the numbers again A to B, you solve it, and you find that your electric field is reducing by S. Okay, you can easily see that S cube by A cube, limits from A to B, B cube minus A cube, right? All this mathematics, it's very easy mathematics. So you will find that your electric field is reducing by 1 by S. So what do you found? Electric field is 0 for S less than 0. Less A. Electric field increases by S square for A to B, and electric field decreases by S if S is greater than B. So how do you find this? How do you plot this graph? This is the graph plot. So this, you see, electric field increasing by S but it is reducing slowly because it is a function of 1 by S. Okay, so this is how you should see the graphs and everything. Very important two problems that you should know, how to solve, and your answer should match with the answers which are given here. Other than this, you should solve all the problems of the Griffiths for the Gauss's law. And few things that you should note here is that you should do by yourself actually is how to find the electric field due to charged wire. So let's say there is a wire having the charge density lambda, means charge per unit length. How do you find the electric field due to this? Second, electric field due to infinitely charged plates. So let's say I give you the charge plate which is infinitely charged plate. What will be the electric field due to this? How do you find this? And let's say I give you two plates. Now what will be the electric field in between here and there, on the right and on the left? These kind of problems are given in the Griffiths and you should definitely know this. These two are actually very, very important and all of you should know the results of this. Exact, it should be on your fingertips actually, these and you should be able to solve these problems very quickly. very quickly. If someone gives you that find the electric field, you must be able to find the electric field because of such charge distributions very quickly. So this was about the lecture 1. What we will cover in lecture 2 is actually potentials. Okay, so today we talked about the electric fields. Now we have to go from electric field to potentials. From potentials we will go to energy, then we will go to capacitance, and then we will go to conductors. So this is how electrostatics works. And then we have some special topics of EMT. Special topics of EMT. For example, dipole moment. For example, electromagnetism in the materials. Let's say you are not in free space, but inside some material. How your electrostatics will change. Then multipole expansion. Then image problem. So these are the special topics of electromagnetism. So in next lecture, we will go for potentials. Then we will go for energy. Okay. So please go through the DJ Griffiths book, solve the problems, read the Griffiths book, and watch this lecture again and again. See these notes in the Telegram channel and get all the results which we have derived today by yourself. And solve the PYQs. PYQ solutions are given to you and it will be updated every day. So today I will give you the PYQ solutions on our JEST course page. Okay, so if you don't know, you have to go to tests.physicsbyrn, tests.physicsbyrn.com, and there is a JEST free course going on there. If you enroll to that course, you can easily enroll by yourself. You can see all the videos, all the PYQ solutions, test series there. Okay, so you can just go and look at it. So today I will update the PYQ solutions of the electrostatics based on the today's lecture. Then tomorrow we will have the live class at 7 p.m. on the potentials, right? So see you all. I wish you all the best. So we will meet tomorrow at 7 p.m.